Welcome to this explainer. Today, we're diving into the actual mathematical magic that powers modern AI. We're skipping the hype and going straight to the mechanical heart of how these systems literally learn. So, let's just jump right in.
Before we get lost in the weeds of giant large language models or self-driving cars, we've got to ask the fundamental question, right? How does a machine actually think? I mean, how can a chunk of silicon mimic a biological brain? Understanding this one thing completely unlocks the mystery behind pretty much every major tech breakthrough we've seen in the last decade.
Here's our roadmap for today. We'll quickly cover the brains behind modern AI, the anatomy of a neural network, and how they actually learn. Then, we'll hit on the big challenge of overfitting, the different types of networks out there, and finally, wrap up with why this all matters so much.
All right, Section 1, the brains behind modern AI. Let's take a quick look at where this wild technology actually began. You know, it's kind of crazy how long this idea has been floating around. The whole thing was directly inspired by biological neurons. Way back in 1943, Warren McCulloch and Walter Pitts proposed the very first math model of a neuron, proving that simple units could actually crunch numbers. Fast forward to 1958, and Frank Rosenblatt introduces the perceptron algorithm, basically a linear model for pattern recognition. And look at today. We've got these massive deep neural networks powering transformers and CNNs. It's an absolutely brilliant evolution.
Moving on to Section 2, Anatomy of a Neural Network. We've got the history down, so let's pop the hood and look at the basic building blocks.
So at its core, a neural network is just a layered machine learning model. It stacks these simple artificial neurons into multiple layers. And what it does is learn pattern-recognizing weights and biases straight from the data you feed it. It really does function a lot like how our own brains digest and process the world around us.
To put that into perspective, let's use a spam filter as our mental sandbox. Imagine an email, the classic Nigerian print scam, gets fed into the network. The raw inputs here are specific words: prize, money, deer, win. The early neurons process those individual signals, and then the deeper layers combine them to capture the whole shebang, the overall suspicious tone of the message.
But wait, how does the network actually know which words are the red flags? Well, that brings us to weights. Think of weights literally like physical dials on a soundboard. They control exactly how strongly each input feature influences the final decision. So the network is going to crank that dial way up for a high-risk word like prize, giving it way more influence than, say, a totally harmless word like hello.
Now, right alongside those dials, we have biases. These are built-in values that essentially shift the decision threshold. In plain English, a bias makes sure a neuron can still activate and do its job in the computation, even if that initial input signal is super faint. It's like giving it a little nudge.
And here's how it all stacks up. You start with the input layer, which is basically just a holding pen for the raw input features, like our email words. But then you move into the hidden layers, and that's where the real heavy lifting happens. These layers apply all those weights and biases to perform linear transformations, magically converting those raw inputs into entirely new, abstract mathematical representations.
Finally, all of that math hits the output layer. This is where the network applies a nonlinear activation function. You'll hear folks talk about tang, sigmoid, or ReLU here to spit out the final prediction. In our spam example, it calculates the exact probability that the email is junk, and boom, flags it if it crosses the line.
Okay, Section 3, how neural networks actually learn. We've got the parts laid out, but how on earth does this machine actually get smart?
It all boils down to a loop of 4 incredibly rigorous steps. Step 1 is the forward pass. Data just flows through the network to make a guess. Step 2 is error calculation. This measures exactly how badly it messed up that guess. Step 3 is the backward pass, or back propagation, where the error travels back through the layers. And finally, Step 4, weight update, where it actually adjusts its internal dials.
We really need to zoom in on Step 3, because backpropagation is, without a doubt, the mechanical heart of this entire explainer. It propagates the error backward through the network. Using the chain rule from calculus, it figures out exactly how much each specific weight and bias contributed to the mistake. It literally traces down exactly which dials need tuning to fix the error.
And playing right alongside backpropagation is gradient descent. This is the optimization method that actually makes those micro adjustments to the dials. By tweaking the weights and biases just a tiny bit in the direction that reduces the error, over millions and millions of passes, the network eventually zeroes in on the perfect setup. It's kind of like finding your way down a mountain blindfolded.
just feeling for the downward slope with your feet.
All right, Section 4, the challenge of overfitting. As miraculous as this whole learning process sounds, it definitely isn't without its hurdles.
The biggest trap here is overfitting. This happens when a neural network becomes way too complex, with just too many parameters. When that happens, it might flawlessly memorize our training data, but then it completely faceplants when it sees a brand new, cleverly worded spam email out in the real world. Basically, it just memorized the past instead of actually learning the underlying pattern.
Because of that, practitioners have to be super careful about managing what's called the bias-variance trade-off. Striking that perfect balance is absolutely crucial to make sure the model actually generalizes well to new, unseen data and doesn't just act like a giant parrot.
Moving on to Section 5, different types of networks. Once you've got those basic building blocks down, you can stack them into some incredibly specialized architectures. This breakdown is great. First, you have convolutional neural networks, or CNNs. These act as the eyes of AI, detecting spatial hierarchies, which makes them absolutely perfect for computer vision and images. Next up are recurrent neural networks, RNNs. They use feedback loops to process sequential data unfolding over time, like speech. And finally, transformers. These are the engines behind modern natural language processing, using attention mechanisms to figure out context and dependencies in language.
Which brings us to Section 6, why neural networks matter. Let's zoom out for a second and appreciate the massive impact these systems are having on our world right now.
Because they can capture these wildly complex, nonlinear structures that old-school classical models just completely miss. Neural networks are everywhere. CNNs are literally driving autonomous vehicles. Transformers are the brains inside your favorite chatbots and machine translation tools. We're using them for financial modeling, weather forecasting, game-playing agents with reinforcement learning, and even heavy-duty fraud and anomaly detection. The sheer scale of this is just staggering.
But here is the kicker. The leap from that simple 1958 perceptron to today's mind-blowing generative AI is really just a matter of tweaked architecture, massive mountains of data, and insane compute power. Whether you're looking at a giant language model writing code or an image generator painting a picture, they are all still relying on those exact same fundamental principles: layers, learned weights, and backpropagation.
So, I'm going to leave you with this provocative thought. If just scaling up these relatively simple mathematical dials can simulate something that looks an awful lot like human reasoning, what kind of crazy new capabilities are going to emerge when we push the architecture even further? As we keep dumping more data and compute into these things, the boundaries of what AI can learn seem almost limitless. Thanks for hanging out for this explainer. I really hope it gave you a clear window into how the machines of tomorrow are actually learning to think.